which penalizes u from differing from the sign of y. So y is a function which takes values plus minus 1 on subsets d plus and d minus of the domain, and we try and choose to penalize in a way that's a continual limit of the discrete problem I described earlier. So this is a nice clean optimization problem. We also have a nice clean probabilistic problem that arises from the small noise limit of both probit and level set, where we can define a Gaussian process on the domain D from which the data is sampled, the unlabeled data is sampled. We have a differential operator which is proportional to the graph Laplacian to the power minus alpha. Sorry, L is a differential operator, C is a covariance operator, which is this differential operator to the power minus alpha. And provided alpha is bigger than d over 2, this Gaussian process, the Gaussian process with this covariance C, that's written here, is supported on continuous functions. And that's a sharp result. And so we can define a large graph limit of both level set and probit methods, which is the clean unifying problem I described to you earlier, but here in a continuum setting. So here we have a Gaussian process with this covariance, and that posterior distribution is that Gaussian process conditioned so that the sign of u agrees with the sign of the label data. I'm just going to finish by showing you a simulation of that process. And then I'll take questions. Tell you what the label data and non-label data is hidden from you. It's recovered from here. The label data is non-label data. It's sampled from the density rho, which concentrates on the folds. One is curve here and a similar curve here. Although it has a constant background sampling density everywhere, but most of the mass is on these two manifolds. And the label data is a small subset up here, which is labeled as +1, and a small subset here, which is labeled as -1. What you're going to see now is the sampling method, which will try and partition the whole domain into +1 or -1 based on labeling here as +1, labeling here as -1, correlation information inherent in the differential operator. But this is essentially a level set method. And this is run at a very fast time scale. I'll show you slower in a moment. These are samples from the Gaussian process. This is the sign of the samples of the Gaussian process. And on the left, this is the time average of that, and this is the time average of that. So we just run that again. And the key point is that what you see on the left here is a partition of the domain into a full labeling of the whole domain. Here labeled as -1, where it's blue. Here labeled as +1, where it's red. And the interface region is the region where we're uncertain about the labeling. And if you recall that my labeled data was concentrated, unlabeled data was concentrated on these two manifolds, you will observe that this interface lies between these two manifolds. I'm just going to slow this down so that you can see that there's an underlying stochastic level set method, which is running behind it. So here you see the level set method. So these are samples of the Gaussian process I described to you, and these are partitions of the domain into labels +1 and -1, with an interface between them. So this is really, this is an underlying level set function down here, which is thresholded to give this partition. Okay, so to finish by just recapping what I said at the beginning. For me, I'm not trying to show you better algorithms to do graph partitioning. I'm interested in mathematical understanding of existing algorithms, in the firm belief that the more we understand algorithms that are used in engineering practice, the more we will be able to improve them in the future. And that may have timescale of decades rather than months. Machine learning as a whole is a field which is very much evolving on a timescale of months and is doing so in an engineering mode. My claim is that mathematicians can help that endeavour by studying and formulating problems of machine learning theoretically, and that will have a long time to have impact. But if you look at the history of, for example, the finite element method, I think you will be convinced that mathematicians investing in understanding engineering practice that's already very successful can have a great deal of impact in the long term. And I would encourage those of you who are young enough and interested enough in machine learning to think about the theoretical end of the subject as well as all the wonderful things you can do by solving problems in engineering practice. Thanks.